Okay, so in the previous example, we went and took the original differential equation, multiplied by an integrating factor, and then made the new equation exact, and then we actually verified that it was exact. So now the last part of this problem is for us to go in and solve the equation. And so the first step is to always take the coefficient on the dx, and you want to integrate that with respect to x. When we integrate it, we're going to get the natural log of the absolute value of x for the first term, and then minus x over y for the second term, and then plus an arbitrary constant g of y for the third term. We now need to take the partial derivative of this function with respect to y and set it equal to the other coefficient. So if we take the partial of f with respect to y for what we just had, the natural log of x disappears, and we're going to have a plus or positive x over y squared plus g prime of y. And again, we always set that equal to the other coefficient, which up there is x over y squared. And again, as we said in the other video for the other problem, you're always going to see these x terms, sometimes called the cross terms, always matching and canceling out of consideration. So if we strike those two terms out, we end up with our g prime of y being equal to 0. That forces g of y to be equal to an exact constant, an ideal constant, if you want to say it that way. So now if we go back to our capital F, we had f of xy being defined as the natural log absolute value of x. And then we had our minus x over y plus our g of y, which we said was k, and that's equal to capital C, because again, this is equal to a level curve. And just like before, you can think of this little k as being absorbed by the c because you don't need two arbitrary constants in one equation. So the final answer then is the natural log of x minus x over y is equal to a constant c. And just as suggested in the other video, you can check your answer by going through and taking the implicit derivative of this, of y with respect to x, and then rewriting it as the original differential equation.